In this video, we're going to be learning about electrolytic cells as well as what to do when we have molten substances involved in our redox reactions. So electrolytic cells is a type of electrochemical cell that requires energy in order to force the reaction to happen, because otherwise the reaction is non-spontaneous. So that's an important distinction that you need to know. You need to be able to distinguish the two different types of electrochemical cells, which are voltaic cells, sometimes called galvanic cells, and electrolytic cells. So electrochemical cells, that's like the overarching or the big umbrella term, and then we can split it up into voltaic, which is sometimes called galvanic, and then electrolytic. So with voltaic cells, those operate using spontaneous reactions, and you get a positive electric potential from these cells. So this just means positive electric potential. Additionally, with voltaic cells, what they're doing is they're taking chemical energy and turning that into electrical energy. So chemical energy gets turned into electrical energy. So E is for energy here. For electrolytic cells, it's pretty much the exact opposite. So these use non-spontaneous reactions, which means they'll have a negative electric potential. And what they do is they take electrical energy and turn it into chemical energy. So again, these E's just stand for energy. Alright, so we've already talked about this here. Voltaic cells spontaneously convert chemical energy into electrical energy. Electrolytic cells convert electrical energy into chemical energy non-spontaneously. Okay, so you do need to be able to differentiate the two types of electrochemical cells, just both theoretically as well as visually. So with voltaic cells, it'll be really easy to see like the two half cells with either a salt bridge or a porous cup connecting the two half cells, whereas for electrolytic cells, because it's a non-spontaneous reaction, you can have the anode, the cathode, and your solutions, all of your electrolyte solutions, all within the same beaker. You can mix them all together because they're not going to react, because it's a non-spontaneous reaction that you need to put in electrical energy in order to force the reaction to happen. So instead of a voltmeter, which you would see in a voltaic cell, we instead have a power source in electrolytic cells. So you need to be aware of that, because sometimes you'll get diagrams and you'll be asked to identify okay, is this a voltaic cell or an electrolytic cell? Okay, so notice that we don't need a porous cup or salt bridge in an electrolytic cell because with a non-spontaneous reaction, we do not need to separate the reactants. So to determine the half reactions for an electrolytic cell, we still do the exact same things that we were doing back when we were talking about voltaic cells. So the first step is still going to be to list our species. Then we're going to figure out what our SOA is and what is our SRA. So the difference that you'll see between voltaic and electrolytic cells by looking at page 7 in your data booklet. So both of these squares are trying to represent page 7 of the data booklet and that redox table there. So if I look at it really quickly, this table right here, what we're going to notice is that for voltaic cells which operate using spontaneous reactions, our OA or our oxidizing agent will be above our reducing agent or RA, and that results in a spontaneous reaction. Okay. So here with this line, this is to represent like the reaction you pick for your strongest oxidizing agent, and that's the reaction that occurs at the cathode. Whereas over here, this will represent your SRA, or your SRA reaction that happens at the anode. Okay, so to determine the SOA, you make sure to create your list of chemical species, and then whichever species or chemical species that you find as you like scroll your finger down the table, whichever species that you run into first on the left-hand side of the reaction arrows, that's going to be your SOA. And then to find your SRA, you put your finger in the bottom right-hand corner and you scroll it up, and whatever chemical species that you hit first on the right-hand side of the reaction arrow, that's going to be your SRA. Now for non-spontaneous or electrolytic cells, for electrolytic cells that run on non-spontaneous reactions, this is going to be the difference. So now what we're going to have instead is our OA is going to be below our RA. Okay, so this results in a non-spontaneous reaction. So I'm abbreviating non-spontaneous just to non-spon, and this means reaction. Okay, so what it's going to look like when you select your chemical species here, let's just highlight this. So your reaction for your strongest oxidizing agent, the reaction that occurs at the cathode, is going to be below your strongest reducing agent reaction that happens at the cathode, or at the anode. Is going to be below the strongest reducing agent reaction that happens at the anode on your redox table there. Okay, so that's going to be the main difference that you see on page 7 of your data booklet when you're selecting your SOA and SRA species for electrolytic cells, okay, compared to what we were doing for voltaic cells. So the only difference is that a voltaic cell uses a spontaneous reaction to produce electricity. An electrolytic cell requires energy to make a non-spontaneous reaction happen. So again, these are just more differences that you need to know between voltaic cells and electrolytic cells. So we've got an electrolytic cell set up here, and we're asked what are the cell reactions and the cell potential of the aqueous potassium iodide electrolytic cell. So first things first, let's list out our chemical species. So we've got potassium iodide, aqueous potassium iodide. So aqueous means that we have water. And then potassium iodide, with that, because it's aqueous, we know it can dissolve in water. And since it's an ionic compound, we know that it's going to dissociate into its ions there. So K plus, aqueous, and iodide ions there. Okay, so we have our species list. Now we need to go to our redox table on page 7 and figure out what is our SOA, what is our SRA. Okay, so looking here, and I'm keeping in my mind, I've got water, potassium ions, and iodide ions. Let's see what we can find first. So for this reaction, yes, it has water, but we don't have this hypochlorite ion. Therefore, we can't use this reaction here. Okay, I'm not going to pick iodine because we have iodide, so I1 minus aqueous, but we don't have I2, so iodine. So I can't pick this one either. So it looks like the first one that we run into is going to be water for our strongest oxidizing agent. Now for our strongest reducing agent. Again, I'm starting in the bottom right-hand corner, and I'm moving up until I hit my first reducing agent. Okay, so then we have our iodide ions right here. So as you can see, our oxidizing agent is below our reducing agent. So this is just what I was talking about up here with this diagram right here. Okay, so let's write out these reactions. Remember, red cat gets fat. Reduction happens at the cathode. So the oxidizing agent helps other things to get oxidized, but it itself undergoes reduction there. So that means I'm going to be writing this reaction for the cathode reaction. So I'm just writing SOA to mean it's this reaction that's happening at the cathode. So 2 waters plus 2 electrons produces hydrogen gas and 2 hydroxide ions. Okay, and then for the anode reaction, so anox gets thin. So at the anode, oxidation happens, so that's going to be the reaction that belongs to your reducing agent, because reducing agents help other things to get reduced, but it itself undergoes oxidation. So we're writing this reaction backwards, so I'm starting from the right and going left to write this out. So starting with the iodide ions. I'm just going to line up the reaction arrows here. Okay, so the next thing that we need to do is we need to figure out what the cell potential is. So what is the electric potential of this electrolytic cell? So we can use this formula to figure that out. So that's just the electric potential of the cell is equal to the reaction happening at the cathode minus it should be the electric potential of the reaction happening at the cathode minus the electric potential happening with the reaction at the anode. So usually I just write this as E net is equal to cathode minus anode, or alternatively, if that doesn't work for you, you could just do SOA minus SRA. Okay, so the electric potential for both of these reactions here. So for our SOA, that was negative 0.83, and then for the SRA, it was positive 0.54. So how you do that, you just plug in the numbers, and these units are in volts. So if we take 0.83 volts and subtract 0.54 volts, then what we're going to get is negative 1.37 volts. Okay, so keep in mind, if you are using the formula, then you're directly plugging in the reduction potentials of both the SOA reaction and the SRA reaction. If you choose to use the non-formula way, then what you would do, so for my SOA reaction, you would write the electric potential as is, because we wrote this as a reduction reaction. But for the SRA reaction, because we wrote it as an oxidation reaction, we're going to have to flip. If you wanted to use this method, you would have to manually flip the sign on it. So since the reduction value for this reaction is positive 0.54, to get the oxidation value or the oxidation electric potential for this reaction, you would flip that positive into a negative. Okay, and then add them up, and you'd still get that negative 1.37 volts. Okay, so we'll call this way the non-formula way. Okay, versus the formula way is over here. So for the formula way, you're taking the numbers directly from the redox table on page 7 of your data booklet, and you're directly substituting them in. Whereas for the non-formula way, you have to remember to flip the sign on the oxidation reaction. So you can choose which one of these methods you want to use. Choose one, stick with it. So we flip the sign on the oxidation reaction when we don't use a formula. So that's why I'm calling this way over here the non-formula way. Okay, Now, talking about this electric potential of this cell, so a negative voltage is telling you that you have or you're working with a non-spontaneous reaction, and that's how you know it belongs to an electrolytic cell. So a negative electric potential means that the reaction is non-spontaneous. So I'm just shortening that to non-spon. All right, moving on. We're asked to predict the anodic, cathodic, and net reactions that occur when electricity is passed through a copper 2 sulfate solution. What voltage would be required to make the reaction happen? So this last part is just asking us to find the electric potential of the cell. So something like this, right? This is telling us that for this previous question, in order to force this reaction to happen, we would need 1.37 volts supplied to this, like each anode and cathode from this battery in order to force the reaction to happen. Okay, so let's start off with our species list. So copper 2 sulfate solution. So solution tells us that we're able to dissolve this in water, and since it's an ionic compound, it's going to dissociate. So we've got our copper 2 plus ions, we've got our sulfate ions. Because it's a solution, we know water is present, and that is everything. Okay, so let's figure out what our SOA and SRA are. So I'm starting out with my SOA, and I'm just looking at the left-hand side here to figure out what reaction I can use. So it looks like the first thing that I run into is copper 2 plus ions. Now I need to find my SRA. So looks like it's down between sulfate ions and water. So it looks like right there is going to be my SRA. Okay, so for my SOA, I'm going to write this reaction from left to right. And then for my SRA reaction, I'm going to write this from right to left. So remember the cathode half reaction, that is your SOA reaction, and then the reaction that happens at your anode is your SRA reaction. And I'm just lining up the reaction arrows to make it easier to see so that I can create my net reaction. Okay, so remember that when we're adding up reactions, the goal is to make it so that our electrons cancel out. So we're asking ourselves, okay, what is the lowest common multiple between 2 and 4? Well, that's going to be 4. So I need to multiply everything in my SOA reaction by 2 in order to make this happen. So 2, that would be 4, this would be 2. Okay, so now we have electrons, an equal amount of electrons on opposite sides of the reaction arrows. Okay, so keep in mind, even for electrolytic cells, you're still looking for one of your reactions to have the electrons on the reactant side and the other one to have the electrons on the product side, because one will say, like, okay, this is the reduction reaction, then the other one will be the oxidation reaction, and you need both in order for a redox. So that's a combination of the words reduction and oxidation in order for both of those to happen. Okay, if you've got your electrons for both reactions on the same side, you're doing something wrong. So these cancel out, and then doesn't look like anything else cancels out, so I'll write the net reaction here. Okay, and for the voltage, I'm just going to go with the formula way. So I'm going to go with E net is equal to SOA minus SRA. So the reduction values for both of those, so that would be positive 0.34 for the SOA and then positive 1.23 for the SRA. Okay, so 0.34 minus 1.23 is going to give us negative 0.89 volts. Okay, so it's going to take 0.89 volts in order to force this reaction to happen. Okay, so we're going to move on to a unique cell for electrolytic cells. So that's important to note that what I'm going to talk about in this section only applies to electrolytic cells. So right here we have something called the chloralkali cell. Okay, now what it does is it electrolyzes an aqueous solution of sodium chloride in order to produce chlorine gas, hydrogen gas, and aqueous sodium hydroxide. Okay, now with this type of cell, let's just list our species. So it electrolyzes an aqueous solution of sodium chloride. So that's what we're starting out with. So if we were to write our species list, I would have sodium ions because this is dissolved in water. So because it's an ionic compound, it's going to dissociate. So we have sodium ions, chloride ions, and because it's a solution, we also have water. Now, because of what's present in our species list here, we run into something called the chloride anomaly. Okay, now let's just look at what we've got and just see where it's sitting in this redox table here. Okay, so we have chloride ions here, water. We also have both chloride and water in this reaction on the right hand side. Okay, and on the left hand side we're going to have our sodium ions. Oh, and then we also have water right here. Okay, so looking at this, our SOA is very clearly going to be water, but for our SRA, water is also appearing. Okay, so that just makes no sense. Like, yes, water appears on both sides, but there's a problem here. Water can't be both gaining as well as losing electrons here. Okay, and so this is where the chloride anomaly comes into play. So water, it is our SOA. However, when you have chloride ions as well as water present in an electrolytic cell, so it's very important that you understand this is only for electrolytic cells, they're essentially going to battle, like chloride ions and water are going to battle to be the SRA, and chloride ions, they will always win. Even though they are higher up on our list of reducing agents, chloride ions will win in this very specific circumstances when you have an electrolytic cell and you have chloride ions and water present in your species list. So the chloride anomaly is when you have chloride ions and water battling to be the SRA. The chloride ions always win. Okay, so then I'm going to label these as SRA down here. So it's very important that you know the chloride anomaly and that you're able to apply it, but you only have to apply it for electrolytic cells. Okay, so for non-spontaneous reactions. All right, so we're asked to predict the voltage necessary to allow the electrolysis of sodium chloride solution to occur. Okay, so let's write out our reactions again. For our SOA, this is the reaction that we're going to use, writing it from left to right. And then for the SRA, this reaction up here with the chloride ions, that's what we're going to be using, writing it from right to left. So I'll put the reduction reaction first. Okay, and the electric potential for that is negative 0.83 volts. And then for the oxidation reaction, that was, I'm going to scooch this over actually. So our chloride ions produces chlorine gas plus 2 electrons. Okay, and the electric potential for that is positive 1.36. But since right now I'm using the non-formula way to figure out the voltage or the net electric potential, and since this is my oxidation reaction, I'm going to flip the sign on this. Okay, so you could choose to use the formula in order to figure this out, and I'll show that in a second, but if you wanted to use the non-formula way, you need to manually flip the sign on your oxidation reaction. So negative 0.83 minus 1.36, that's going to give us negative 2.19 volts. Okay, So again, this is the non-formula way. If you wanted to use the formula way, then what you could use is this. So E net, you can choose to go cathode minus anode, or you could do SOA minus SRA. You can choose which one of these you like best and go with it. Okay, I'm just gonna go with the SOA minus SRA just because it's the last one I've written. But if you wanted to see how to do this with the formula, you just write in the reduction values as they appear on the redox table. The reason why you can do that is because you have a negative in the formula that's gonna do the flipping of the signs for you. So we'll call this formula way. I'm not writing the net reaction for this because the question didn't ask me to write the net reaction here, but I did just want to write out what the reduction reaction was and what the oxidation reaction was that we were using. All right. So with voltaic and electrolytic cells, like I've been saying, it's very important that you understand the difference between the two and you're able to identify a voltaic cell versus identifying an electrolytic cell and know the differences between the two. Okay, so for voltaic cells, those are going to use spontaneous reactions, whereas electrolytic cells use non-spontaneous reactions. For the net voltage for voltaic cells, that's going to be positive, whereas for electrolytic cells, it's going to be negative. Forever and always for electrolytic cells, it will be negative, and forever and always, voltaic cells will have positive voltages. For the energy conversions for voltaic cells, that's chemical to electrical. So chemical energy to electrical energy, whereas electrolytic is the opposite. Okay, so what's the point? That's basically just asking, okay, what do we use it for? Okay, so for voltaic cells, we use those as batteries. And something called a sacrificial anode, which we'll learn in a future lesson. Whereas for electrolytic cells, they are useful when you're doing something called electroplating, which is essentially you're covering an object with a pure metal. That's what electroplating is. And with electrolytic cells, they are useful for rechargeable batteries. So when I said batteries before for voltaic cells, I'm meaning the regular ones that are not rechargeable, whereas electrolytic cells, those are your rechargeable batteries. Okay. So direction of ion movement, for both of them, the cations are going to migrate towards the cathode, and your anions are going to migrate towards the anode for both. Okay, so these are going to be the same. For direction of electron flow, it always starts at the anode and goes to the cathode for both. So these electrons, they're traveling through an external wire that connects the anode to the cathode. Okay, if we were to draw a picture of this, we're going to have this. We have our salt bridge. We have one of our electrodes. We'll say this is the anode. And then the other electrode, we'll say this is the cathode. And so they're connected by a wire that has a voltmeter, so that's an instrument that measures volts. And the electrons go from the anode to the cathode. So here's we have both of our solutions in each of these beakers. That's the salt bridge. There we go. Okay, whereas for an electrolytic cell, we've got one beaker here. There's our solution with everything in it. Here's one of our electrodes. Here's the other one. We'll say this is the cathode. That's the anode. Here's the wire, and the wire is going to have a battery connected to it. So the way we represent a battery in these types of circuit diagrams would be like that. Okay, so each pair of a short stick with a long stick, each of those are like a cell. So this is a power source. So it could be a battery. But electrons still flow from the anode to the cathode. Okay, moving on to molten substances. Molten, all it means is liquid. However, there's not going to be any water present. So a molten ionic compound still splits into ions, kind of like it does with an aqueous solution. However, very important that no water is listed in your species list. Okay, so this means the products of the reaction are different when you have a molten substances versus if you had the exact same thing with an aqueous substance. Okay, so for example, we got to write the cathode, anode, and net reactions for the electrolysis of molten aluminum oxide. So the species present, if we have molten aluminum oxide, so aluminum oxide, that's an ionic compound, and since it's molten, that tells us, okay, it's going to be dissociating, so it's going to be splitting apart into its ions. Remember, when a substance dissociates, you're only ever going to have two products, the cations, the positive ions, and the anions, which are the negative ions. Okay, so species presence, we have aluminum ions and oxide ions. The cathode reaction is going to be aluminum, whereas the anode reaction is going to be the one with the oxide ions. So our net reaction is as follows. Okay, so just notice here that because we have a molten substance, we're using the state liquid. So if you have something whose state is usually aqueous or solid, and you're given a question where it's like, hey, the substance is actually molten, then you need to write it as a liquid. So you're going to have to pay very close attention to the wording of the question, because it will tell you if your substance is molten or aqueous. Okay. If you have something that's a gas, it's going to stay a gas. So here you can see oxygen gas, like it doesn't turn molten as well because gases can't do that. All right, so we have another example. What are the products of the electrolysis of molten potassium iodide? So because it's molten, and this is an ionic compound, that means it's going to dissociate, and I got to remember to put them as liquid. Okay, so for our cathode reaction and our anode reaction, we need to find those. So let's clean this up a little bit. Okay, so potassium I know is down here. Okay, and iodide. I don't think iodine is here, but on the left-hand side, but iodide, the ion, is not. Yeah. Okay, and we're not going to select water because this is a molten substance, but there's no water present. Okay, so now I'm looking at the right-hand side, just picking out what I have. So we got that. Okay, so the reactions I'm going to write this reaction from left to right because that's the SOA. And then I'm going to write this reaction from right to left because that is my SRA. Okay, so I will write the net reaction for this here. So since we got the same amount of electrons but on opposite sides of the reaction arrows, don't have to multiply anything. So those cancel out, and now I can just write the net reaction here. Honestly, probably the trickiest thing about this would be remembering to write the liquid state for your molten substances. And there you have it.